So our second speaker today is our new sponsor from Impress Software, Simon Davidman, who's the president and CEO. He's going to talk about the art and science of automating verification checking. As I mentioned, he's the CEO Simon of Impress, an initiator of open virtual platforms. He has worked on simulations and EDA products since 1978. Prior to founding Impress, Simon founded Co-Design Automation, the developer of the System Verilog language, and has also been an executive or European GM with 5 EDA startups, including Chronologic and Ambit. He's also based in the UK. So over to you, please, Simon. Thank you.
Great. Yeah, thanks, Mike. And so can you hear me okay, yes?
Yes, go ahead.
Okay, so yeah, as you say, Mike, we just joined as a sponsor of the DV Club, and so we've been involved. Obviously, a company we're over 10 years old in simulation and verification for a long time, and in the RISC-V world, which is where we actually spend our time in terms of verification. What we saw is that there was a lot of people looking into the ISA, a lot of people trying to do the hardware design, but actually no one was really looking at how verification of processes should be done as a public thing. Up to RISC-V, it was really all proprietary inside the companies, in the Intels and ARMs and people like that. And so that's why Imperius, we're focusing on verification of RISC-V. That's why we're sponsoring things like the DV Club, because we think there's a lot of activity happening around verification generally. And as Mike said, I've been involved with verification for a long time, including System Verilog. But in the RISC-V world, there needs to be a lot more discussion and awareness. And so that's why we're talking more about sort of RISC-V and its verification. But here I'm going to talk really about how technology can help with the verification checking. I'm not sure about the art and science of automating, but I think when it comes to verification, actually, yes, there's science in it, but actually a lot of it's creative. And so I quite like the concept that it's a bit of art and a bit of science. And this is the abstract that we put together. And just looking at the bottom, it's really the things to focus on are the specification of what's needed for verification. And then we're going to talk today here about generators around coverage and how those are being used in some of the technologies that we're involved in. So, as we're all involved in verification, there's a lot of people on this call, and we know there's never enough time. Electronic products need more and more verification, and of course you have less and less time to do it in. And it's okay saying, hey, great, there's the cloud out there with infinite resources, but actually you need stuff that you've got to run on this cloud. It's no good having 1,000 machines that you can use. You've got to have technology and stuff to run on it. And where does that stuff come from that you have to? Well, you've got to create it, right? And so what have you actually got to create? So you've got to create your verification plans, and they really are the thing which drive the goals. And every good verification project should have verification plans as a starting point to really scope and bound what's going to be verified. And then you have to get your sort of predictors or your reference models that you're going to compare against and verify your design against. And obviously they need configuring and things like that. So you either develop them or you acquire them or find them available. Then you've got to create all your scoreboards to record and compare what behavior you're seeing during verification. And actually, of course, this is about dynamic verification, not static or formal, which was the subject of the previous presentation. We're focused here on verification using simulation and dynamic verification. So you need to get a reference. You then got to get the scoreboards, which can actually record and compare the functionality that you're seeing. Then you need functional coverage, which is the way of measuring progress against your verification plan. Then you've got to get test benches to run them. Then you've got to get test programs to stimulate them. And of course, when you've got all that, then you can just run this stuff in the cloud. If you've got, but you have to get all this. And if we just look in terms of an example around RISC-V processes and the design verification of those, there are several things you need. Okay, so I mentioned, yes, you need your verification plans, and then you're going to need some form of test to come in, whether you handwrite them as directed or whether you write them with an generated by an instruction stream generator. Then you have your sort of test bench, which in a commercial world, most of it's System Verilog that's used out there. And so you have to get your RTL, you have to be loading programs into the memory, you have to be running it under some form of control. And the key thing from a verification point of view is you've got to have some verification IP, whether you create it yourself or you license them. As I mentioned, you need a configurable reference model, you need some form of synchronization, which we'll talk a little bit more about with asynchronous stuff. You need your scoreboard, you need to know whether the test has passed or failed, and then we're going to talk a lot about the functional coverage. And these verification IPs have to somehow interface into the core through what's commonly now being called as a tracer. And there are other things like virtual peripherals to do with logging and maybe generating interrupts and things like that. So these are the sort of main components that one might find in a RISC-V processor DV environment. And you've got to create this stuff. And the bits here, which are sort of outlined in black here, are the things that need creating or acquiring or configuring before you can really start. You assume you've got your core and you've got some test bench which runs out Hello World or something. But to do real DV, you need all these other things associated with it. So let's talk about where automation can help and get these things for you. Well, okay, so these are the things that we said that we needed to do. And if we just look at these, so in terms of a reference model, obviously Impirus, we're a commercial vendor, you need to get access to a reference model, and we'd like to license our technology to you. We actually also make some available for free, but really you need a high quality reference model if you're trying to do processor DV, and it's got to be very configurable and integratable, because you actually want to get it into this environment where you can be running it with the rest of the things that are running in there. So the first thing you need is to get hold of a reference model, which is going to predict the result that you should be getting from your design. Now, in terms of the scoreboards where you're recording things and comparing, that sort of stuff should all be able to be automated because the processes are well defined. So that should be automatable. The functional coverage, which I'm going to talk a bit more about now, is, that of course can be automated as well. Test benches, and the idea is if you use sort of standards and higher level reusable verification IPs, then you should be able to get test benches up and running really quite quickly. And then you've got to get your test programs. And a lot of that can be done nowadays with generators for processes. So there's 5, 6 different things that you have to get together. Several of them can be automated and several of them can be sort of acquired in or brought in. So you normally can get up and running really quite quickly. But what we're going to focus on now is the functional coverage aspects of it. That's the bit with the verification, automatic generation of this verification checking around the functional coverage. So what we're going to talk about is 4 or 5 things related to this. So functional coverage is a component that's going to be in the test bench, and I'm going to go through the different bits to start talking, just give an overview of what we're really talking about here. Now, if you've been doing verification using System Verilog, all of this should be well known to you. But basically, you have to run your design with some form of tracing information through some interface to some functional coverage. You'll then get some coverage data out to analyze. So in the System Verilog world, these are called cover points and cover groups. And there's an example of them here in System Verilog for a simple add instruction. And what happens is that this System Verilog effectively connects through the tracer to the core, where things are sampled when things like instructions retired, or there are events triggering things in the test bench to do with interrupts or asynchronous events. So there's the System Verilog cover groups and cover points that are needed. And then you need to run it with a tool from Cadence, Synopsys, Siemens, EDA, Metrics, which will then run the simulation on the sample points, extract the information into the data files, collate it after many runs, and then you get a report to see at the end how well your coverage was, what you've done. And then because your verification plan helps you write your coverage points, when you're getting close to being done with your design. So that's sort of an overview of System Verilog sort of functional coverage here. Now, what requirements does that put on a test bench? Well, functional coverage only tells you what is actually being seen in the test bench and the design under test. It doesn't tell you what your RTL actually did what you expected. And that's where the reference model comes in, and the scoreboards and comparators and all the verification IPs come in. they allow you to run the simulation and check that it's doing what you expect. And that means your functional coverage then becomes meaningful. So just be careful. Having functional coverage doesn't mean to say the design is doing what you expect. It's just saying you put in a large collection of tests effectively in there. And for the verification to be good and the coverage to be meaningful, you have to have the appropriate components into your test bench. And today in sort of process of DV, there are several different type approaches people have, from simple self-test, which is, it runs a simple ad program or whatever, where you can check the output yourself with the self-test in there. So that's one approach. Another is where people use sort of file compare, where like in the compliance group for RIS5, they do that where you dump out a signature, and then after the simulation, you compare that with the signature from your RTL and with the reference. Another alternative is where you trace a lot of log information into a log file to do with instructions that have executed values and things like that. And again, you create files for your design, files from a reference, and do post-simulation comparisons. The challenge with those, I mean, this isn't the subject time to get into that subject, but there's lots of challenges with these sort of simplistic approaches. A more sophisticated approach is where you do co-simulation and you're tracking things when synchronous events happen, and in the most advanced environments, asynchronous events. And it's very important that you use an appropriate test bench for the level of verification you require. Because, for example, if you're really trying to test asynchronous behavior, you just can't do that with these simple approaches, which means you might have great functional coverage saying, oh, I've checked all my interrupts and everything. But actually, if you haven't compared to the quality, to the reference, what you're doing, it's actually pretty meaningless in there. So you've got to make sure you have an appropriate test bench. And if you want to do things like asynchronous, you need one of the more sophisticated asynchronous lockstep compare sort of types of approaches. So it's important you need more than functional coverage in there. Now, let's talk about functional coverage around RISC-V here. So what are the requirements? Well, there are several different areas here. So for example, in the basic instruction set, you've got all the instructions in what we call unprivileged execution modes, and you have sort of standard processor state and simple modes. But whenever you design your own design, you're going to put your own pipelines, you've got your own architectural, micro-architectural choices in there. And there's a lot of things that can be selected in the RISC-V ISA. I think in our reference simulator, there's 300 or 400 different options you can choose about how you're setting things up, whether registers are read-only or whether you've even implemented the status registers and things, which interrupts you've got, whether you've got to debug. There's a tremendous amount of flexibility and configuration in there. And you need to make sure that you've covered what's in your design, whether it's simple things like the basic ISA, or whether you want to check how the things are going through your pipeline and the DV hazards and all this type of stuff in there. And so there's a lot of stuff that has to be put into the functional coverage. And if we just look at sort of some of the numbers, in RISC-V, in the RV64, 64-bit, there's almost 1,000 instructions in the basic. It's not just basic, there's actually only 50 odd in the basic integer. But when you add in the mass, the compressed, and the floating point, and the crypto and things, you end up with almost 1,000 instructions. And if you've got to write that system Verilog coverage information, there's probably 10 to 40 lines of system Verilog for every instruction. You're into the tens of thousands of lines of Verilog you have to write and get working, to get the basic stuff up and running, to verify that your design is being tested the way that you're expecting to test it. So there's quite a lot that needs to be done to get you up and running. So it's not a good idea to try and write those 40,000 lines all by hand, right? So what we've done in Imperis, we built some technology which generates all of these checkers, this system Verilog functional coverage. And this is really an overview. And this is not a product we sell, and I'll explain. We basically give away the functional coverage that we create because we found it very useful ourselves, and also our customers have found it very useful. So we're as part of the community, we're doing this. But so we talked a little bit before, you're going to have a core, you're going to have a tracer, and then you've got to do some functional coverage. And some bits of the functional coverage have to be handwritten, which basically do the interface to the core. And then on top of that, there's all the different extensions that are available in the RISC-V world. And we have a tool which allows us to take a machine readable internal format, which defines the instruction set and all the privilege modes and everything. And then we configure this tool and we can write out a system Verilog source file for the integer of a 32-bit, or the maths, or the compressed, or the floating point. So we can generate automatically all of this system Verilog functional coverage, from the simple stuff all the way into the more complicated things to do with memory protection, exceptions, interrupts, and all the way through it, and even some user-defined instructions we can do as well there. So this is the type of flow that we use in Pyrrhus to do this. So I'm just going to dig down into a couple of these things. First, the internal format that we use for this machine readable. And as I said, we've got to try and generate tens of thousands of lines of system Verilog. So we need a very good representation of what is a processor, a RISC-V processor. What are its instructions and things? So there are several categories of data that we have in our format. There's all the ISA extensions and the groups. And the key thing is the version revisions, because RISC-V is an evolving technology. And so every few months, there's a different extension changes or adds, and they ratify 10 to 20 a year now. So there's a lot of change. So our technology has to understand what version is being targeted so it can get the right information about the instructions, their format, and what coverage we're after, and the buckets and things that need to go in there. So the simple stuff, we can also get into the control and status registers and specify those. And those get very sophisticated because a lot of them could be read-only or read-write. They can have many different fields, and each can have different coverage requirements in there. And that all interrelates to how the interrupt and debug mode has been implemented in the core. And the challenge for RISC-V is a lot of this is very optional and configurable. And so you have to have quite a sophisticated representation to capture all of this sort of configurability. And it actually gets more complex than that, because a lot of it can be context aware. So if you're in a certain mode, certain things become available. For example, you can switch from 64-bit to 32-bit dynamically. Well, that means all of the status registers and everything can change size. And so there's a lot of complexity, and it's not just a simple static thing that has to be specified here. And then it gets a bit more sophisticated, because the specification allows people to have user choice in there, make things implementation defined. So you can choose things in there. And just to get close to sort of wrap up here, so in use, we've been using this internally. We originally developed this under a contract. We had a contract to develop a vector test suite for RISC-V several years ago, and we had no idea what the coverage was. So we had to build some coverage technology. And then, there's 350 odd vector instructions. So we really didn't want to do all this by hand. And then we did that, and we made actually the 32i available publicly in open hardware. Used that in the first core that they developed, the 32E40P. Used the first generation of this. We provided the system Verilog source in there. We worked with the architectural group, test group in RISC-V International, and built basically coverage into all of our simulators. But that's binary, that's not system Verilog. But again, it's using the same representation. And where we are now is that we're working on developing all of the system Verilog source. And the first few files have already been released in our products and made available to people. And it's using a standard which is evolving around RISC-V for the interface. And it's been done in UVM, so it can be extendable. And there's a new project starting up in open hardware to try and add requirements for the DV side of things. And so just to wrap up here, so if you can generate these verification components, you can provide significant benefit to the DV teams. You don't have to, every team, create 40,000 lines of code in there. You've got to have machine readable formats as inputs to these generators, and we're still capturing requirements on more of the DV side of things. And we've been using this for several years in this technology, and our roadmaps to make more and more of the system Verilog stuff available as open source, and we've already started doing that. So it should be usable by any processor project with RISC-V. And with that, I'm done. Thank you very much, and hand back to you, Mike, for questions.
Thanks, Simon. Yeah, we've got a couple of minutes for questions, please. So the first one is what format is the machine readable specification or reference? What format would you recommend for that?
Right. Okay. So it's the format that we use is not a public format. It's something we've created. There are several people are trying to do it in the RISC-V community. There's one called RISC-V config, which is a YAML-based one. There's another one done by RISC-V org, which is actually in it's their own format. We tend to use a mix of Python and YAML, Python structures if it's dynamic or YAML if it's static. But there's no consensus yet on the content or the format, but I expect that to happen over time because the industry really does need a common machine readable format.
Okay, and there's some publicly available that people can use and then do their own automation off that machine readable format.
Yes, there are a couple out there. Yeah.
Okay, I think we'll end there, Sam. We've got another couple of questions, but maybe we'll put those to you offline.
Send them to me. I'll do them offline. I'll get someone to answer them. Thank you very much.
Well, thank you very much, Simon, for your first talk. All very good. Thank you very much.
Thank you, Simon. Appreciate that.